You know, there's this ghost in the machine of the modern web. We don't really see it anymore, or at least we try not to, but you can definitely feel it.
Oh, yeah.
It's that tiny bit of lag.
Hmm.
It's hitting refresh on a sports score, you know?
Yeah.
That sort of subconscious feeling of just waiting for the server to notice you.
It's the legacy of a web that was built for documents.
Yeah.
I mean, the whole idea was like a digital library. You go, ask for a book, you read it, and if you want an update, you have to go back and ask for the whole book again.
Right. It feels so archaic when you put it like that. But then you open something like a stock trading app or a multiplayer game or even just Slack, and all that friction is just gone.
Mhm.
The data is just there. It feels like the server is reaching out to you.
Because architecturally it is. We've moved past just fetching things.
Mm-hmm.
We're talking about opening a persistent tunnel and leaving it open.
And that is exactly what we are unpacking today. We're doing a deep dive into WebSockets. But I want to be clear, we're not just, defining the buzzword. We've got a whole stack of implementation guides and architecture diagrams here. The mission is to really understand the engineering that kills the refresh button.
We're going to get into the packet structure, the handshake, and the actual back-end setup you need to make this work at scale.
Okay, so let's start with that fundamental shift. The source material draws this really hard line between classic HTTP and WebSockets. They call HTTP request response.
Right, and to really get why WebSockets are such a big deal, you have to appreciate just how inefficient HTTP is for anything real-time. It's unidirectional.
Meaning what, exactly?
The client talks, the server listens, then the server talks, and the client listens. They can't speak at the same time.
It's like a walkie-talkie where you have to say over after every single sentence.
It's actually worse than that. It's like a walkie-talkie where after you say over, you have to throw it away, buy a new one, and tune it to the right frequency all over again.
Because it's stateless.
Exactly. So if you want updates, like for a stock price, you have to do what's called polling. You're just constantly asking, anything new? How about now? Has it changed yet?
Which brings us to what the docs call the aha moment. WebSockets are described as full-duplex.
It's a two-way street, a bidirectional highway. Once that connection is open, the client and the server can both push data at the same time whenever they want. There's no more asking.
And there's this amazing visual in the notes here about the efficiency gap. It's not just about the connection, it's about all the baggage.
Yeah, this is something a lot of developers miss early on. They think, oh, I'll just pull the server every second. It's a tiny request, but it's really, really not.
No, this breakdown is kind of staggering. Every single HTTP request carries this huge block of headers. You've got cookies, user agent strings, accept headers, refer data.
I mean, the source notes that to send just one byte of data like the letter A, you might be wrapping it in 800 bytes of headers.
800 bytes of metadata for 1 byte of payload.
And if you're polling every second across thousands of users, that's a massive amount of wasted bandwidth. It's like sending a semi-truck to deliver a single envelope.
So how does the WebSocket frame compare?
Well, once that tunnel is open, you strip all of that away. The source highlights something like a 95% reduction in overhead. The header on a WebSocket frame is just a couple of bits. It's incredibly lean.
That 95% figure, that's the key takeaway. That's why this powers things like high-frequency trading. You literally can't afford the latency of repackaging HTTP headers every few milliseconds.
Speed is a product of efficiency, yeah. But here's the catch. The entire web infrastructure routers, firewalls, you name it, is built for HTTP. You can't just invent a brand new protocol and expect it to work.
Which is where the handshake comes in. I love this idea. It's basically a Trojan horse.
That is a perfect way to describe it. To start a WebSocket connection, you first have to pretend you're a normal HTTP request. The client just sends a standard JDT request. To any firewall, it looks totally normal.
But inside that request are these special upgrade headers.
Exactly. The client sends connection, upgrade and upgrade.websocket. And, most importantly, it sends a sec WebSocket key.
I saw that in the spec. It looks like an encryption key. Is that what it is?
That's a really common misconception. It's not for encryption, it's for verification. The client's basically saying, hey, I'm a real WebSocket client, not just a confused browser. The server has to prove it understands the protocol.
So how does the server prove it speaks WebSocket?
The server takes that key, it appends a specific magic string, this globally unique ID from the spec, hashes the result with SHA-1, and sends that back in the sec WebSocket accept header.
It's a secret handshake.
It really is. And along with that hash, it sends back the status code 101 switching protocols. And that 101, that's the green light. At that exact moment, the rules change. The TCP connection stays open, but we stop talking HTTP and start talking WebSocket binary.
Okay, let's look at that binary. The source material breaks down the frame architecture. This is where we get down to the bits and bytes.
Yeah, this is the low-level stuff. We're not just sending JSON strings anymore. We're sending packets defined by individual bits.
The first thing I see is the FIN bit, just one bit right at the front.
The FIN bit, yeah. Short for final. It's super simple. 1 means this is the end of the message. 0 means there's more coming in the next frame.
And that's for fragmentation, right? If you're sending a huge file or something.
Exactly. You don't want to block the whole pipe with one giant message. You chop it up. The receiver just buffers all the frames until it sees one with the FIN bit set to 1, then it sticks them all back together.
And then there's the opcode, only 4 bits.
The opcode just tells the computer how to interpret the payload. Opcode 1 means it's text. Opcode 2 means it's raw binary data.
And there's one for closing the connection, too. I saw you don't just, hang up the phone.
Right. Opcode 8 is a close frame. And that's really important for handling errors cleanly. It lets the client and server say goodbye politely and explain why they're disconnecting. It's much better than just a crash.
Now, there was one security feature in the frame that seemed a little odd to me. The masking bit. It says all frames from the client to the server have to be masked. Why is that?
Okay. So this is a defense against a very specific kind of old vulnerability called cache poisoning.
Cache poisoning.
Yeah, imagine you're on a corporate network with a transparent proxy server. If a client sent unmasked data that happened to look like a valid HTTP request, the proxy might get confused and cache it.
And then it might serve that private data to someone else by mistake.
Exactly. It's a mess. So the mask scrambles the data, the client generates a random 4-byte key and XORs the payload with it. To any intermediate proxy, the data just looks like random noise, so they ignore it. It's a clever bit of engineering to work around old infrastructure.
Okay, that makes sense. So we've got the tunnel, we've got the packets, let's build something. The source has this great case study for a real-time weather alert system.
This one is perfect because it really shows why you need to separate your concerns. You can't just bolt WebSockets onto a traditional web server.
Okay, so the architecture has 3 main parts: the publisher, the broker, and the subscriber. Let's start with the publisher, which is a Django app in this example.
All right, so Django is your normal web app. It handles business logic, databases, users. In this scenario, the Django app figures out, uh-oh, a hailstorm is coming. It needs to send an alert.
But Django is mostly synchronous. It's not built to hold open thousands of persistent connections.
That's the core problem. If you tried to make Django manage the WebSockets directly, the whole server would just grind to a halt. So Django doesn't talk to the user, it talks to the broker.
And the broker here is Redis PubSub.
Yep, Redis is the glue. It's an in-memory message queue. Django just publishes a message to a Redis channel, say weather Nike, and its job is done. Fire and forget.
And on the other side of Redis, we have the subscriber. The notes use Starlet for this.
Right. Starlet is a Python framework built for async. It speaks ASGI, not WSGI. It's designed from the ground up to handle thousands of open connections at once because it's non-blocking.
So Starlet is the one actually holding all the connections open to the user's browsers.
Correct. The browser connects to Starlet. Starlet subscribes to that Redis channel. It just sits there listening. The moment Django drops a message in Redis, Starlet grabs it and immediately pushes it down the right WebSocket to the browser.
I love that decoupling. It means the main Django app doesn't even need to know WebSockets exist.
It scales beautifully. You can have one Django app and 50 Starlet servers. It's totally modular.
Now let's flip over to the client side, the browser. The source calls this client-side reality. It's not magic. And the JavaScript for it looks almost too simple.
It is. The browser API is great. You just say new WebSocket, give it a URL, and then you define listeners. On open, on message, on closed. It's very event-driven.
But there's a huge warning in the production notes here about reconnection logic.
Yes. This is the big one. This is the thing that gets everyone.
With HTTP, if a request fails, you just hit refresh, right?
Exactly. But with a WebSocket, that connection is a living thing. If your user walks into an elevator and their Wi-Fi drops for 10 seconds, that TCP connection is severed. The on-close event fires. And then nothing.
Wait, the browser doesn't automatically try to reconnect?
Not at all. If you don't write the code to handle that, your app just dies silently. The screen freezes. You have to implement what's called an exponential back-off algorithm.
Why exponential? Why not just retry every second?
Because if your server crashes, you might have 50,000 clients disconnect at once. If all 50,000 try to reconnect at the exact same moment a second later,
You DDoS yourself.
you DDoS yourself, you crash the server again. Exponential backoff means you try right away, that wait 1 second, then 2, then 4, then 8. It spreads out the load. It
Yeah.
is absolutely mandatory for any real-world app.
That's the kind of detail that separates a demo from a real product. Speaking of which, we have to talk security. The source outlines a 3-layer defense.
Security is tricky because a lot of standard web security relies on HTTP headers, which
Yeah.
we're not using after the handshake.
Layer 1 is origin and host validation. This is to stop something called CSWSH.
Cross-site WebSocket hijacking. It's like CSRF, but for WebSockets. Imagine I run evil-site.com. You visit my site, and my JavaScript tries to open a WebSocket to your bank server using your browser's existing session cookies.
That sounds bad.
It's very bad. But the defense is easy. During the handshake, the browser sends an origin header. Your server just has to check it. If the origin isn't on your allow list, you send back a 403 forbidden, and you never upgrade the connection.
Simple enough? Okay, layer 2, authentication. And this is where that weird API quirk comes in. You can't add custom headers.
No, you can't. It's a known limitation of the browser API. Normally with a REST API, you'd send an authorization, bearer header with a JWT. The new WebSocket constructor just doesn't let you do that.
So, how do you authenticate?
You pass the token as a query parameter in the URL. So it's wss.api.site.com/socket.token.
Isn't putting secrets in a URL generally a bad idea?
It is a trade-off. It's safe on the wire because you're using TLS, but yeah, you have to be very careful not to log those full URLs on your server. The server code has to grab the token from the URL during the handshake, validate it, and only then proceed with the 101 upgrade.
And that brings us to layer 3, encryption itself, TLS.
This is just non-negotiable. You have WS, which is plain text, and WS dot, which is encrypted. It's the same as HTTP versus HTTPS.
And the source is blunt. Never use WS in production.
Never. Just don't. Always use MyS. You can terminate the TLS at a load balancer like Jinx, but the connection from the user to your infrastructure must be encrypted.
So we've covered a ton of ground. But let's land on the trade-offs. The source ends with a big reality check, the cost of real time.
This is so important. WebSockets are powerful, but they are expensive. And the number one cost is that they are stateful.
Right. We said HTTP is stateless. Fire and forget.
With WebSockets, your server has to hold that TCP connection open in memory. It has to keep track of every single client.
So if you have 100,000 users online, your server is actively managing 100,000 open connections in RAM.
Yes. And that has huge implications for deployment. If you restart your server to deploy new code, you just hung up on 100,000 people at once, you get a thundering herd of reconnections. It's a serious DevOps challenge.
And you lose out on caching, too.
Totally. You can't put a CDN in front of a WebSocket conversation. Every single message has to go all the way back to your origin server. There's no caching it.
So this all leads to the final strategic decision framework. When should you actually use this?
The decision tree they give is pretty simple. Ask yourself, am I just doing SEO root operations? Am I fetching a resource like a blog post or a user profile? If yes, use HTTP. It's stateless, it's cacheable, it's easy.
But if you need that live interaction...
If you need latency under a second, or you need the server to be able to push data without being asked, think collaborative whiteboards, chat apps, financial tickers, then and only then do you reach for WebSockets.
It's the right tool for the right job.
Precisely. WebSockets solve the latency problem. They are not a replacement for HTTP.
A really solid place to land. But before we go, I want to leave everyone with that provocative question from the end of our source material. We just talked about the stateful nature of this.
The scaling problem.
Exactly. If every single user needs a dedicated slot in your server's memory, how does your architecture have to change when you go from, say, 10,000 users to 10 million?
That's the C10M problem, handling 10 million concurrent connections. Keeping that door open for everyone might become too expensive.
So is that persistent tunnel always sustainable?
Not always. Sometimes knowing when to close the door is just as important as knowing when to open it.
Something to think about. Thanks for walking us through the real-time web.
My pleasure.
We'll see you on the next deep dive.